Okay, so we are the Automatic Fisherman Group, also known as Fishies. My name is Tanner Smith. This is Brendan Harrod and Daniel Scott here with us. So we appreciate the time, and we're excited to talk about our project. We believe that it will enlighten your mind. So you might be wondering how a bunch of engineers are going to apply fishing to process control, but we're going to debunk that myth. So I was born and raised in Florida, and had many interactions with many different fish over my life. So I've fought some big ones, and most of the time those big ones got away. And so that brings us to our project motive. So everyone has a story when they're catching a fish. It got away, the line broke, and so we're going to mitigate those risks and be able to come back to all right, what's going on, kind of eliminate the problem of the line breaking, and use process control to catch the fish every time. But it also applies to rigs on oil platforms. So if there's a hurricane coming through the Gulf, how do you know how much attention the line to provide attention to have the rig stay in place or give it slack so it can oscillate with the wave oscillations? And so that's where we get our project motive, and we can start from there.
All right, so as with any control system, your sensor, your actuator, and your controller. So our sensor, when we actually implement this, we're going to use a fiber optic strain gauge, and that will constantly monitor the tension in the line. For the actuator, it'll just be the reel. It'll be connected to the boat, and we'll just have a simple PID controller connected to that. For the system parameters, the control variable that we're going to have is going to be the tension in the line. Initially, we had started with looking at all the possible sources of force, and it was a three-dimensional momentum balance, and it was a really big pain. So we simplified it into just a one-dimensional problem for this project, and for future development we can expand that into second and third dimensions. For the manipulated variable, it'll just be the real speed of the motor, and we'll be able to vary that, as you'll see in a couple slides, with a slave controller. It'll vary the voltage to the motor to get the specified RPMs. And for the disturbance variable, it'll just be the movements of the fish on the end of the line. And because the fish's movements are random, essentially, it was kind of difficult to model. So what we decided to do is to use a sine function. And that way we kind of get a minimum and a maximum force that the fish could exert on the line. It kind of gave us a range to work with. So in developing our model, we have our two graphs here that represent the open loop and closed loop, open loop tests for both the process and the motor. And as you can see, we got a really, really good fit for both of those. For the process, you can see it's linear, and that's what we expected. We were happy to see that when we were developing this, because our model is based upon Hooke's law, which is a linear model. So moving on to the next slide, we have kind of an overview of what our PID control system looks like. And as you can see there in the center, we have the inner loop, and that controls the RPMs of the motor. It receives a set point, an RPM set point from the process controller, and it iterates the voltage to meet that RPM specification, and then spits it out and runs all the way through.
Alright, so we wanted to make sure that our process is actually modeled compared to our experiment, and if our control tuning parameters are actually valid. So you see here that we have like 0.14 for our process gain, and then for our motor gain is 0.009 and 0.517 for the time constant. So what we decided to do is do root stability analysis on this. So we took the product of these transfer functions, and we were able to gain a root stability analysis. And since that was a sixth-order transfer function, it looked a little bit different from what we saw in class. But what was really interesting was that at 0.4508, we found out that's the max on our stability. And that actually was modeled really closely to what the system actually did. So we decided to do a selective gain of 0.14 to account for disturbances, and we also discovered that if we use some, I guess, more complicated models for motors, no matter what we did, it was inherently unstable. So we took a simplified motor transfer function, and it worked quite well. Here's the experiments that we did with the actual simulation. So here we see at a gain of, let's say, about 0.4, that's what the experiment was. We actually see stability at the end. At first it had some pretty bad oscillations, but at a gain of 0.6, it was inherently unstable, which matches the root stability analysis. Here we were able to take a look and see how we can make our system a little bit better, a little bit worse. So if we had a ratio of the amplitude, let's say pound for pound, what the fish is going to do, or let's say the fish can give 100 pounds for every pound that the motor could do, well, what would happen? So we see here that if we had a really strong fish, it would actually affect the performance a little bit. The rise time would decrease, the settling time would not actually be applicable, and if we did, let's say, 100, no matter what the motor did, that the line would break, because that would make sense. There's a limit to what you can actually catch. So your motor can only do so much for you, so you can't go catch a marlin with a 2-pound line. So again, that fits in real life in our motor, in our simulation.
But there are further developments that need to be accomplished here. So just as Brendan said, we can't catch a marlin on a 2-pound line, but if we can better model that fish, and we know marlins will pull and rest and pull and rest, and that's the reason for our sine function. So a better development of the motor and a better development of what the fish is actually going to do. Maybe a feed forward to kind of predict what the fish will do will give us better results and be able to catch a fish a lot bigger than this one.
Thank you.